Okay, so let's talk about the question marble mischief today. Jake has 200 black, 400 white, and 600 green marbles in a container. He draws the marbles one by one without putting any back. What is the probability that at least one white and one green marble remain in the container right after the last black marble is drawn? Okay, so there's kind of two approaches to this question, but both of them, the idea behind this question is um you kind of want to have you kind of want to like basically think of it as only looking at the marbles that you care about and the remaining doesn't matter. And you always want to look towards, like, for instance, if you were just looking at two colors and then the other one doesn't matter, then just ignore the other one because it doesn't matter where those are placed, right? So that's like one big takeaway from this. The second big takeaway approach is like sort of um kind of just looking at the last condition, like the last marble condition, and then kind of working from there. Because once the last marble condition is satisfied, everything else should be satisfied. So that's kind of the approach. And there's kind of two ways of doing it. One with like De Morgan's law and inclusion exclusion principle, and the other is more unique and simpler with the law of total probability. Okay, so let's dive in and see how it works. So we can first define the events in our first approach with so we're going to let EW be the event that at least one white marble remains, and then EG be the probability that at least one green marble remains. So basically, the problem is just asking us for the probability that EW and EG. But EW and EG are hard to calculate. So we're going to transform that to finding complements. So we're going to use De Morgan's law, and we're just going to do PEW and EG is equal to 1 minus the probability of the complements union. So that's kind of what we're going to do. And we know that the complement union can be rewritten using the principle of inclusion and exclusion as the following. So that's kind of what we're trying to find. So we're trying to find um, this, this, and this. These three things. And then we're just going to 1 minus these things. Oh, 1 minus the following formula here. And we're going to get our answer. So kind of the trick here is to ignore the irrelevant marbles for each subproblem because it's not going to make a difference. So in our first thing when we're trying to find the complement of W. So that's the idea that there's no more white marbles remaining after the last black marble. So that means that basically the last marble has to be black, right? So the probability of that being drawn is just basically there's 200 blacks and then there's 600 things, right? So then the probability is 200 over 600. So it's one third. And then the same idea with the greens, but just the last marble is still black, and then the greens, there's 600 of them, so the denominator is 800, and it's one quarter of the probability. And then this, both of them not satisfied. So this means that there's a total of 1,200 marbles, and then the last one is black. So that's 1/6. So basically, we just put these values back, plug it in, we find that our final value is 7 over 12. So that's pretty straightforward. I think the major thing was just kind of knowing that you had to find the complement because it's too hard to find the thing directly, and then ignoring the irrelevant marbles. The second one is, I think, a bit more neater. So it's called using law of total probability. So this kind of avoids the principle using principle and inclusion and exclusion. So here we know that we're going to set up P and G. Um, G and W, basically G just means like the last marble, like the very last marble is green and the very last marble is white. Because if the last marble is black, there's no way we're going to satisfy the criteria, right? Because there's nothing remaining. So it has to be either green or white. So then the probability of drawing a green at the end of the thing is 600 over 1,200, which is one half. And the probability of getting white is just 400 over that. So it's one third. Yeah, here we see black is excluded because it's not possible. And then next, we're going to try to find the conditional probabilities. So B given G. So this means that we're going to need the very last marble drawn to be green so that we make like because we assume that that's the case because that's the case. And then we would want like the last black marble to be drawn. When it's the case, we're going to have once something with white in between that, right? So in order for the last white marble, we're just going to ignore the green. Like just take out all the greens, and then we just have black and white. If we have black and white, then the last spot of that has to be white in order for the thing to work. Because if a black was at the end, then that means no white was at the front. And if a white is there, then it definitely satisfies no matter how many other sequences there are. So basically that means that the last marble has to be white. If the last marble is white, there's 600 of them because 200 plus 400 is 600. And there's 400 whites. So then that's just 2/3. And then the same with the thing with white, because we're going to need the last, out of just excluding the green variables. I meant like excluding the white variables. Then we have the green and the black. With the green and the black, we want the green to be the last one. So that would just be 600 over 800, which is 3/4. So then we just apply the law of total probability. PB is equal to we're just forming a partition of G and W, each one with their respective probabilities. We just plug in what we just found into these, and we get that it's over 7/12. So I think this is probably the best approach to go with this problem because it's pretty nice, and I think it's relatively easy to calculate the probability. The major takeaway, of course, from this problem, no matter which approach you take, is that you kind of ignore the irrelevant marbles. Okay, let's end off here.